Testing, can you hear me? Testing again, can you hear me? Alright, this video is public now, so I'm going to be reading the introductory statistics book again. Last stream I finished reading about descriptive statistics. This stream I'll be learning about probability topics. Okay. Alright. Uh, let's start with the terminology chapter. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. The result is not predetermined, then the experiment is said to be a chance experiment. Flipping one fair coin is an example of an experiment. Uh, okay, I will just write the terminology stuff here. So I will do leftwards. The result of an outcome, the result of an experiment is an outcome. The sample space of an experiment is the set of all possible outcomes. Three ways to represent the sample space are to list the possible outcomes, to create a tree diagram, to create a Venn diagram. The upper letter S is used to denote the sample space. Let me copy this. Just copying the definition stuff. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if an experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written PA. The probability of any outcome is a long-term relative frequency of that outcome. Probabilities are between 0 and 1 inclusive. Probability of A0 means that event A can never happen. 1 means event A will always happen. 0.5 means event is equally likely to occur or not to occur. Long-term frequency. Should I write that? I should write that. Equally likely means each outcome of an experiment occurs with equal probability. For example, if you toss a fair six-sided die, each face 1, 2, 3, 4, 5, or 6 is as equally likely to occur as any other face. You toss a fair coin, a head and a tail are equally likely to occur. you randomly guess the answer to a true or false question on an exam, you're equally likely to select a correct answer or an incorrect answer. Calculate the probability of an event A when all outcomes in the sample space are equally likely. Count the number of outcomes for event A and divide the total number of outcomes in the sample space. For example, if you toss a fair coin and a fair nickel, the sample space is HHTH, HT, and TT, where T is states and H is head. So you're tossing two coins, and these are the four possible outcomes. Uh, so let's say A is getting one head. There are two outcomes, so the probability of A is 0.5. The important characteristics of probability experiments is known as the law of large numbers, which states that as the number of repetitions of an experiment is increased, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. To the theoretical probability. I'll just shorten this. I think I should write it like this. Even though the outcomes do not happen according to any set pattern or order, the long term observed relative frequency will approach the theoretical probability. The word empirical is often used instead of the word observed. It is important to realize that in many situations, the outcome are not equally likely. A coin or die may be unfair or biased. Two math professors in Europe had a statistics student test the Belgian €1 coin and discovered that in 250 tries, a head was obtained 56% of the time and a tail 44%. The data seemed to show that the coin is not a fair coin. More repetitions would be helpful to draw a more accurate conclusion about such bias. Some dice may be biased. Look at the dice in a game you have at home. The spots on each face are usually small holes carved out and then painted to make the spots visible. Your dice may or may not be biased. It is possible that the outcomes may be affected by these light weight differences due to the different numbers of holes in the face. The outcome is in the event A or B. If the outcome is in A, is in set A or in set B, or is in both A and B. The event A or B can be written as A union B. For example, A is 1, 2, 3, 4, 5, and B is 4, 5, 6, 7, 8. A union B is 1, 2, 3, 4, 5, 6, 7, 8. So 4 and 5 are not listed twice. And event and outcome is an event A and B if the outcome is in both A and B at the same time. Let A and B be 1, 2, 3, 4, 5 and 4, 5, 6, 7, 8 respectively. Then A and B is 4, 5. Complement of event A denoted A prime consists of all outcomes that are not in A. Notice that A probability of A and probability of not A is equal to 1. So let S, so the sample space is 1, 2, 3, 4, 5, 6, and the event A is 1, 2, 3, 4. So not A is 5 and 6. Probability of A is 4 over 6. Probability of these four numbers out of these six numbers is 4 over 6. Probability of not A is 2 over 6. The conditional probability of A given B is written as P. Probability of A given B. Probability of A given B is the probability that an event A will occur given that event B has already occurred. A condition reduces the sample space. I think a better explanation would be um hold on. I can see my It. I think my tablet is not working. I have to use my mouse then. Hold on just a minute. Okay, I will just use my mouse then. Suppose. Where's the circle? Suppose this is the sample space. And within the sample space, we have the event A and event B. Event A contains the number 1, 2, 0 outside. And then there is also an intersection. So 3 is over here. 4. I'm just randomly guessing. 5, 6, 7, 8, 8, and 9. Okay, so we have, wait, also I need to mention that this over here is event A. This over here is event B. So, and the entire thing is the sample space. So probability of A occurring within the sample space is the probability of these 6 elements occurring. So 6 over 10. And then we have probability of B, which is, of course, there are 5 numbers in B, 5 over 10. Now we have probability of A given B. Probability of A given B means if I guess a random number, if probability B already happened, so it's so the number I'm guessing is definitely one of these 5. What are the chances of A happening? So A can only happen, event A can only happen if the intersection happens. So basically, probability of A given B is the probability of intersection over B. So 3 divided by 5. So out of 5 total elements, these 3 happen. Knowing that these 5 definitely happen, if these 3 happen in particular, then we know A happened. So probability of A given B is the probability of the intersection divided by the probability of B. It is important to read each problem carefully to think about and understand what the events are. Understanding the wording is the first very important step in solving probability problems. Reread the problem several times if necessary. The sample space S is the whole number starting at 1 and less than 20. So S is between 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way till 20. And A are even numbers, so 2, 4, 6, 8, all the way till 20. And B are numbers greater than 13. So 13, 14, 15, all the way till 20. Probability of A is 50. Wait, not 50%. 0 is not included, right? No, it's not. Yeah, so probability of A is 50%. Probability of B. So there are 7 numbers greater than 13 and below 20 and below or equal to 20. So 7 over 20. So probability of A and B. So that will only be true if the numbers are 14, 16, 18, and 20. So 4 numbers. So 4 over 20, right? And then A or B. So the 7 numbers above 13 as well as the even numbers below 13. So 2, 4, 6, 8, 10, 12. So 6 plus 7, right? 13 over 20. 13 over 20. A naught is the set of odd numbers. Probability of A naught is also 50%. The sum of their probability is 1. Uh, oh, wait, it doesn't include 20. I forgot. So everything is over 19, not 20. Also, one more thing I want to talk about. So probability of B over here, B given A is 3 over 6, which is 50%. And probability of B normally is also 50%. Probability of A normally is 3 over 5, and probability of A given B is 3 over 5. If probability of A doesn't change, even if B happens, if B happening doesn't change the probability of A, then we say A and B are independent. Also, one more thing. This also means the probability of B also won't change. So probability of B also wouldn't change. This is true because probability of A given B is equal to probability of A and B divided by probability of B. So if this part is true, that B happening, that doesn't change the probability of A, then we can say this, right? And then we can say this A and B. So I'm putting A probability of A and probability of B. I'm exchanging places with them. I'm just rearranging the equation. So this is true about probability of B, right? So then we have, by definition of conditional probability of the intersection divided by probability of A, right? So if this is true, if probability of A given B is equal to probability of A then probability of B given A is equal to probability of B. A being independent from B means B is independent from A as well because these two did not change. When my tablet is not working for some reason, let me see if I can do something because I want to write down some equations. Some reason it doesn't detect it. Okay, never. I'm spending too much time on this site. Let me see if there is anything else I could do. Never mind. So the next topic is about independent events. So over here, if this is true, that A and B are independent, then they're called independent. They're independent events. Uh, also, if I do this, if I have two events A and B, A, let's say they share nothing in common. B, so I have 1, 2, 3. Let's do 4. So 4 possible outcomes. 1 and 4 belong in A, 2 is nothing, 3 belongs in B. Let's do 5, 6 as well. If there is no overlap between them, then we say that these two probabilities are mutually exclusive. Over here, when we want to find the probability of A or B, then that's like there are 10 elements. Probability of A is 6 over 10. Probability of B is 5 over 10. The thing is, we cannot just add 6 and 5 because the intersection will be added twice. Hold on. Probability probability of A or B is equal to probability of A, which is 6 over 10, plus probability of B, which is 5 over 10. But the thing is, there is an intersection, so the intersection gets counted twice. So we need to get rid of the 3. So we need to subtract 3 over 10. A and B. Yeah. So this is the probability. Now, if A and B are mutually exclusive, so A and B is 0, then A probability of A or B is just probability of A plus probability of B. We can just simply add them this time. Two events A and B are independent events if the knowledge of one does not occur, does not if the knowledge of one occurred does not affect the chance of the other occurs. For example, the outcomes of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability of the outcome of the second roll. To show two events are independent, you must show only one of the two of the above condition. If two events are not independent, then we say that they are dependent events. Sampling may be done with replacement or without replacement. With replacement, if each member of the population is replaced after its pick, then that member has the chance of being chosen more than once. Without replacement, each member of a population may be chosen only once. So, if it is not known whether A and B are independent or dependent, assume they are dependent until you can show otherwise. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes, and A and B is equal, probability of A and B is equal to 0. Suppose the sample space from 1 to 10, let A be this and let B be this, and C is this. A and B is 4, 5. Probability of A and B is 2 over 10 is not equal to 0. Therefore, A and B are not mutually exclusive. A and C do not have any numbers in common, so A and C are 0. Therefore, A and C are mutually exclusive. If it is not known whether A and B are mutually exclusive, assume they are not until you can show otherwise. Okay. If my tablet was working, I could have done some of these examples. But most of this is revision, so it's not going to be an issue for me. If A and B are two events defined on the sample space, then A and B is equal to probability of B times probability of A given B. It is by definition of conditional probability. A and B are independent, then probability of A given B is equal to probability of A. And then A probability of A and B becomes probability of A times probability of B. Okay. Wait, I need to write this down. Then this is true. And probability of A and B becomes probability of A, probability of B. If A and B are defined on a sample space, then probability of A or B is probability of A plus probability of B minus the intersection. They're mutually exclusive, then we just add them. Yeah. Wait, what? Uh, yeah. Contingency table. A contingency table provides a way of portraying data that can facilitate calculating probabilities. The table helps in determining conditional probabilities quite easily. The table displays sample values in relation to two different variables that may be dependent or contingent on one another. Suppose a study of speeding violations and drivers who can use cell phones produced who use cell phones produce the following fictional data. Cell phone while driving, does not use cell phone while driving. Speeding violation, no speeding violation. Total. The total number of people in the sample is 755. The rows total 305 and 450. Columns totals are 70 and 685. You notice that, yeah, this and then this. Find probability driver is a cell phone user. Driver is a cell phone user. So 305 divided by 755, right? Find probability driver had no violation in the last year. 685 divided by 755. Find probability that the driver had no violation in the last year and was a cell phone user. No violation and uses cell phone. So 280 over 755, right? Yeah, 280. Find probability driver had no violation in the last year. Okay. Driver is a cell phone user or driver had no violation in the last year. Wait, driver is a cell phone user. So 305. Or driver had no violation in the last year. So this plus this plus this. 685 plus 25, right? So that's 710 over 755. Yep. Driver is a cell phone user. Kevin, driver had a violation in the last year. So out of the 70 people, find probability that driver is a cell phone user. So 25 over 70. Yep. Driver had no violation last year. Kevin, driver was not a cell phone user. So 450 do not use cell phone. No violation. So 405 divided by 450. Okay. Tree and Venn diagrams. Sometimes when the probability problems are complex, it can be helpful to calculate the situation, to graph the situation. Tree diagrams and Venn diagrams are two tools that can be used to visualize and solve conditional probabilities. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make probability problems easy to visualize and solve. Following example illustrates how to use a tree diagram. In an urn, there are 11 balls. 3 balls are red, 8 balls are blue. Draw 2 balls, one at a time with replacement. So, initially there are 8 and 3. So, if I take one ball out, no wait, 3 and 8, okay, yeah, 8 and 3. If I take one ball out, if I take the red ball out, then 8 blue, 3 red. What? 3 balls are red and 8 balls are blue. Oh, it's with replacement. So after my first draw, there'll be 8 blue balls, 3 red balls. After my second draw, maybe 8. Okay, this is not a good example. There is, what is this, 9 R24 RB. First set of branches represents the first draw. Second set of branches represent the second draw. Each of the outcomes is distinct. In fact, we can list the red balls as R1, R2, R3, and each of the blue ball as this. Then the 9 RR outcomes can be written as this. Okay, so I can pick red the first time or I can pick red the second time. There is 3 over. Okay, I will try to draw with my mouse now. 3 over 8. 8 plus 3 is 11. 3 over 11 chance. And 8 over 11 chance of picking blue. Red and blue. Okay, so I have this. So there is 3 over 11 chance of picking red. And there is 8 over 11 chance of picking 8. Sorry, picking blue. If I do pick blue, then there is 8 over 11 chance that I would pick blue, 3 over 11 chance of picking red. Since this branch and then this path, like these 4 events, like all of this will happen after this and they're independent as well, right? So 3 over 11 times 3 over 11 will give 3 times 3 is 9. 9 over 11 square for red, red. 3 over 11 times 8 over 11 when it gives. I give what? What's the. Wait, what? 3 times 8 divide, divided by. Okay, never mind. What is 11 square again? 121. So 24 over 121 of picking red first and then blue. And then we can multiply the probabilities to calculate blue then red, and then we can multiply the probabilities of calculating blue and then blue. Irana has 3 red marbles and 8 blue. Draw 2 marbles one at a time. This is without replacement from the urn. Without replacement means you do not put the first ball back before you select the second ball. So the first red has 3 over 11 chance. Once you pick the first red, then the second row has 2 over 10 chance. So there are 10 balls remaining, and only 2 of them, only 2 of them are red. The rest are 8. The rest are blue. Of course, we can also pick blue marble first with 8 over 11 chance. If we do pick this first, then there's 3 over 10 chance of picking red and 7 over 10 chance of picking blue. The probability of blue first and then blue second is this path 8 over 11 times this path 7 over 10. We have, oh yeah, this event over here. So for this event over here is probability of R given blue on the first draw. I think this should have different labels P1 and R1. probability of R, given that blue is picked once. And then if we want to do by definition of our AND, probability is by definition, right? I'll write it here. So P, probability of R times it with probability of P given R is equal to by definition of conditional probability. And R, P, B first. No, R first and then B. Right. But if we want to get the total and probability of picking, like after two draws, probability of R and B, we have to find the probability of R1, R in the first row, and B in the second row, and then add it with this probability. Add it with probability of B first and then R second. Since BR is independent from RB, we can add the probabilities. They're mutually exclusive because both can't happen at the same time. Probability of Fn or NF. Or we just add them. A litter of kittens available for adoption. The Humane Society has 4 tabby kittens and 5 black kittens. Family comes in and randomly selects 2 kittens without replacement for adoption. 5 over 9 and then 4 over 8, 5 over 9 and then 4 over 8. 4 over 9, 5 over 8, 4 over 9, 3 over 8. What is the probability that both kittens are tabby? So probability of this and then probability of this. 4 over 9 times 3 over 8. 4 over, actually 1 over 2 times 3. So 1 over, where is it? Yeah, it's option C. What is the probability that one kitten of each coloring is selected? So either T and then B or B and then T. So 4 over 9 plus 4 over 9 times 5 over 8. 4 over 9 times 5 over 8 plus 5 over 9 times 4 over 8. So option D. C and then D. Yeah. A Venn diagram is a picture that represents the outcomes of an experiment. A generic consists of a box that represents the sample space S together with its circles and ovals. Circles or ovals represent events. Oh, I already showed this. So event A is this, event B is this, and of course there's the intersection. And 10, 11, 12 are not in any event. So C and PT. Person with type O blood and a negative RH factor can donate blood to any person with any blood type. 4% of African Americans have type O blood and a negative RH factor. 5 to 10% of African Americans have the RH minus factor. And 51% have type O blood. Type O circle represents the African Americans with type O blood. Oh, so the O circle represents African Americans with type O, and then RH minus oval represents African Americans with RH minus factor. We will take the average of 5%, 10%, and use 7.5 as the percentage of African Americans who have the RH minus factor. Let O be the event of type O and R be the event of RH. So probability of O. 5 to 10 have RH minus factor. 51 has type O. So probability of O is 51%, right? And we are using 7.5. Probability of R is 7.5. How do we find this? 4% have type O and negative RH factor. So O and R is 4%. And then how do we find OR? OR is 51 plus 7.5 minus 4, right? So 0.75, 4%, 54.5. Okay, I think this is the last topic, just the key terms. Right, I will end my stream here then. And yeah, I might study more computer architecture next stream. Well, depending on whatever my mood is. Anyways, see you guys next time then. Bye.